All right. So as I was saying, I have pictures. This is my great student, Ellen, and she has the blame of this talk. So okay. So what this is about is we were set to actually to continue a work that Alex Lutke and Lucy Lee started about 2 or 3 years ago, where they were trying to figure out whether there was a structure to problems of inference, compounding data, integrating data, individual level data from different sources. Okay, so the work that I'm going to present is actually generalizing the work that they did, the really pioneer work that they did, and trying to generalize it in a direction that appears to be a bit more challenging, but fits many scenarios that appear in practice, okay, with studies in practice. So let me explain you what in this little vignette, I'm going to try to explain you what the setup is. So suppose that ideally we would have a random sample from a population, and in each individual in the population, we would measure a vector W of comprised of k variables. Okay, and our goal would be to estimate a parameter, a functional of the data generating process of W. Okay, of the distribution of W. But unfortunately, we do not have access to this random sample. Instead, we have access to samples from different sources. Okay, those samples are not even necessarily random samples, okay, simple random samples from different sources. And in each source, we measure perhaps a subset of the variables, and we are prepared to assume only that certain conditional distributions of marginal distributions pertaining those variables that we measure in each source agree with this conditional distribution of W, okay, the conditional distributions or the marginal distributions of W in the ideal data, in the ideal population. So here is an example. Suppose that I have source 1, and in source 1, we observe the subvector W1, W3, W5, and we are prepared to assume that the distribution of W5 given W3 and W1 agrees in that source, agrees with the distribution of W5 given W3, W1 in the ideal population. Okay, that's the only thing we are ready to assume for source 1. Let's say that for source 2, we measure W2 and W6 now, and we are prepared to assume, for example, that W2 given W6 coincide, align. Okay, when I say align, it means coincides. And then in source 3, let's say that we measure the same variables as in source 1, but this time, what we are prepared to assume is that the distribution of W3, see, we are switching now, okay, W3, given perhaps that W5 is equal to a particular value, not the entire conditional, just conditional on a particular value, and W1 agrees with Q, with the distribution, sorry, in the ideal data, and perhaps also the marginal of W1, okay? So this is a scenario similar to the one that Lee and Lutke consider, except of the following very subtle point, not that subtle, but complicating point, which is the following. If you consider the distribution of W, you can imagine factorizing the distribution of W, okay, as the product of, every conditional, into its probability, what is it? The factorization of the joint, okay? The problem is that there is no factorization of the joint that will have simultaneously the distribution of W5 given W3 and W1 and the distribution of W3 given W5 and W1, okay? So what happens now is that the alignments, okay, that we are assuming hold in the sources do not conform a particular factorization do not agree with factors of a single factorization of the joint distribution. Okay, so that's key, because this it's not what Alex and Lucy assumed. They assumed that there was a factorization, okay, and in every source, certain factors, okay, of the joint factorization agree with the sources, okay, with the ideal data, okay. Now this um, weakening of the assumption, or this facilitating this extra, flexibility is important, because there are several examples, especially in complex epidemiological designs and in problems with measurement error and validation studies, external validation studies, where you cannot find, a joint distribution that, where the factors, what I just said, okay, that don't fit the Lucy and Alex. Okay, so let's try to see then what kind of data do we have in hand. The data that we have in hand, indeed, can be seen as, when we pull all this data together, it's like a random sample from the observed data, and the observed data is a Corsen data. We can think of it as a Corsen vector, where S indicates the source, and C is the Corsening function, indicates the part of W that we see in source S. Okay, so C of WS for the first source will be W1, W3, W5. It's a subset of W that we see. Okay, and this observed data has a certain distribution that we call it P. Okay, you're going to call Q the distribution of W, P the distribution of O. All right? Okay, so let me give you a vignette of where we are going. Okay, so here is where we're going. Ideally, if we had data from the ideal world, a random sample from W, we would assume perhaps a model, an ideal data model. Maybe the model doesn't impose any restrictions. Maybe it's a semi-parametric model. Maybe it's a parametric model, some model, okay? And then for that model, we have a target parameter, which is some functional that we are going to assume it's finite dimensional, of the distribution of the ideal data. Q is the distribution of that W that I said before, okay? And that's the ideal target parameter, the one on which we want to conduct inference. And the problem is that in most problems of interest, at least in causal inference and problems that I care about, this target parameter depends on Q through conditional distributions, through high dimensional nuisance parameters, okay, that are either come in the form of conditional densities or conditional expectations that cannot be estimated without many assumptions, without making assumptions, cannot be estimated at rate root n, okay? And the problem with that is that if we want to do just plug-in of this, it is well known that the plug-in estimators, the estimators where you plug in the Q, with the Q hat, okay, or whichever parts of the Q that the functional depends on, that plug-in estimator tends to inherit the bias that is due to the estimation of these high dimensional nuisance parameters. This is completely known. For those of you guys that are going to do 583, you're just about to learn all of that stuff, okay? Of those of you that have already learned it, you know it. Okay, so what we know is that when we have this situation, what we do is we actually use the influence function, which is a functional, it's a random variable that depends actually on the particular functional that we care about, okay, that I'll explain in a minute. And we use this influence function in a particular way. There are many strategies for this. We can do one-step estimation, TMLE, etc., to actually correct the bias of this functional, okay? All right, now, the problem is we don't have the ideal data. So what do we have? We have alignment assumptions, okay? And the alignment assumptions actually impose a model on the observed data. O is now the observed data. Remember that Corsen data, which has a distribution. The distribution here is called P, the distribution of the observed data. And this observed data model might be restricted, might satisfy equality constraints, even if the ideal data model is non-parametric. For example, in the simplest case, suppose that in source 1 and in source 3, for example, the marginal of W5 agrees, okay, with the source distribution, the target distribution, the ideal distribution. So that means that in source 1 and in source 3, okay, the conditional distribution of W, what did I say, 5? W5 given S equal 1 and W5 given S equal 3 agree. That's an equality constraint, okay? That's the simple constraint. But in these kind of models where there are mismatches in terms of the alignments, the kind of constraints that are inherited here can be very complicated, okay? And that actually creates trouble at the time of conducting inference in the following way. So from the observed data model, of course, if we want to be able to conduct inference about this parameter, that is the one that we care about, it better be that this parameter depends on Q only through the aligned conditionals, okay? Because otherwise I cannot identify it, okay? Which is an assumption that we're going to make, okay? So this parameter is identified through the aligned conditionals, and therefore we have a parameter phi p now that depends on the law of the observed data, okay? But this one, if this one had trouble, this one is even more complicated, okay? It has all sorts of, it usually requires all sorts of estimation of high dimensional nuisance parameters. So we also want to calculate its influence function. The problem with this, okay, and this is basically where we contribute, is that typically, because this model is very complicated, calculating from first principles the influence function of this target parameter is complicated, okay? It's not impossible, you can do it, okay? You can do it by hand and spend pages and pages and pages, or you can do it cleverly because you see the structure of the problem. And this is exactly what Ellen has done, okay? And what I'm going to talk about, which is coming from a full data or an ideal data influence function, which we are going to assume it's not that difficult to calculate, okay? We're going to teach you how to calculate observed data influence functions, okay? Influence functions based on the observed data, okay? So that's the task. Really, this part is everything, okay? But we not only do that, we also calculate the efficient influence function. And for those of you that know 583, the efficient influence function really is the one that you want to use, if you can, to get the semiparametric efficient estimator, okay, or semiparametric efficiency, okay? So it's the one that will be pulling the information properly, okay, cleverly, so that it pulls the information from all the data sources so as to estimate this target parameter that is identified by this in the best way. And calculating that efficient influence function, I hope to get to that point in the talk today, you'll see it's complicated, okay? And often, it's not clear even how to do it, but with this template that we have, we know how to do it. Yes? The one is because it's a derivative. The influence function is like a functional derivative, so it's like a one. It's a derivative evaluating at Q, okay? We think of this as a functional function from the model to the reals, okay? This is the derivative, okay? We'll get to that at some point in the talk if I manage to. Okay, so what I'm going to do is I'm going to start with a simple example to convince you that this is useful, okay, and that that there are examples. Then we're going to give you exactly what that first vignette was about, but formal. Okay, we're going to give you the formalism of the framework, then the main result on how to obtain influence functions in the observed data from the ideal data and the efficient one. I'm going to give you 3 additional examples that will actually highlight different issues about this problem. There are many nuances in this problem, and then a discussion. Okay, so here is the first problem. Very simple. It's a simplified version of a setting more complicated. By the way, the paper that it's in the archive has many more examples and more sophisticated examples than the ones we are describing here, okay? But this is a simple example that will make the point, hopefully. So suppose that you want to, you have a target population you want to estimate the prevalence of a certain disease in that target population, but to measure that disease, to actually record the presence or absence of the disease, the gold standard test is very expensive, okay? And you are in a resource-constrained environment, and you don't have access to that test. You only have access to a cheaper test, okay, an imperfect test that I'm going to call V, and you can measure covariance, okay? So in the target population, you can actually get a random sample of V and X, okay, where V is the imperfect test, X are the covariates, okay? And of course, because the target population, you took a random sample from the population that you care about, the alignment is that the marginal distribution of X and V agrees with that of Q, okay? So far, so good. Source one really is the target population in this case, except that we don't get to measure the Y, okay? So far, so good? Okay. Now suppose that we have a second source, which is from an external population, where we were able to run a validation study. We were able to measure the true covariate, the gold standard, the imperfect test, and the covariate, okay? But we are prepared to assume only that what transfers to the target population is the sensitivity and specificity within levels of the covariates, okay? The distribution of V and Y are binary, okay? So the probability of V equal 1 given Y equal 1 and X is the sensitivity, okay, within levels of X, and likewise for specificity, okay? So we are prepared to assume that. And what we want to estimate is the mean of Y, okay? This is what we really want to estimate, but in our source, we never measure that, okay? We only measure it in the validation study. So far, so good? Okay, so the first question you may ask is, well, is it identified? Can I say that the distribution of Y, the marginal distribution of Y depends on Q, the marginal distribution because Y is binary, it's the entire probability, right? That the probability of Y equals 1 depends on Q only through these two alignments, okay? And the answer is yes, so long as V and Y are correlated, are dependent given X. Of course, if you had a V that didn't provide you any information about the gold standard, of course, you cannot hope to estimate anything, okay? But so long as V has some information about the gold standard, you actually have information, and you have identifiability, and there is information, and you can estimate it at rate with n. So let me show you the identifiability for this problem so as to move forward into the part that matters, okay? Remember, I told you that my first assumption was that the target functional psi of Q depended on Q only through the aligned conditionals, okay? The aligned distributions. So I have to show you that it's the case, okay? So what I'm going to do is the following. Suppose that I consider this integral equation. This is an integral equation because it has an integral here, and you have m of xv times the density of xv given xy, okay? And you say that that's equal to y. So you find this m. Well, this m, you can actually, because y and v are binary, it's very easy to find the formula. I could write it, but it doesn't make any point. I could write it because it's simple. I mean, it's not the point. If x and v if v and y are dependent, you can get it. Okay, it's close enough to the type of functionals that you get with instrumental variables, but I'm not going to go any further. Okay, so then we know that the expected value of y, of course, is going to be the expected value of these quantities, because I told you that they are the same at mq. Okay, so far so good. Okay, but that's just the expected value of NQ, of course, because I have double conditional expectations, okay? But now I say, look, wait a minute. MQ is really identified from what? From this validation study. Because in the validation study, I can estimate the distribution of V given X and Y. Remember, V given X and Y, the distribution of V given X and Y in the validation agrees with Q given of V given X and Y. All right? Am I okay? All right. So in fact, this is the same as the expected value of what I would get if I replace by the distribution of V given X and Y, okay? So I'm just looking now at the source 2, okay, the validation study. And then I say, but wait a minute, now I have to marginalize over a function of X and V. Well, I know that the marginal of X and V on Q is the same as under P of S equal 1, okay? Because remember, my source 1 was the actual study, okay, the target study. So then there you go. Now I have a functional that depends on the two sources, on the distributions of the P's on the two sources. So far, so good? Okay, now bear this in mind. Here is the phi of P. So now let's look at what we would do if we would just do plug-in. What would be a plug-in? A plug-in would just do the mean, the empirical mean over the distribution of X and B in source 1 of whatever my estimator of F is that I will get from source 2. Okay? And that would be the plug-in estimate. All right, but that estimator, as I said, typically inherits the bias in estimating this quantity and does not converge at rate root n. So what do? We do the one-step bias estimation, and we could do targeted maximum likelihood. I'm going to focus on one step because it's easier to explain. But what is that? That's a new estimator that takes the plug-in estimator and adds a term. Okay, this term depends on the influence function estimated, because the influence function, this phi1 is the influence function of phi evaluated at p hat. Okay, not at p because we don't know p, it's p hat. And this is typically the bias correction, the one-step estimator. Okay, all right, why is this clever? Why does this work? Basically, and this is my one-dime, explanation of influence functions. I cannot go any further. Why does it work? Because influence functions, okay, influence functions are like first-order derivatives. Okay, so they are like act like first-order functional derivatives. So what you have here is like kind of Taylor's expansion, okay, of the functional phi p. P is like my x, okay? It's like, think of a function of x, a function of p, okay? Evaluate it at p0, that's p hat, okay? P0 times plus the integral. This is acting like the derivative, and this is like x minus x0, okay? That's the dp p minus p hat. And then there is a remainder that is second order, okay? But influence functions, we take them without loss of generality to have the integral of phi1 p hat dp hat to be 0. In other words, the influence functions evaluated at p have mean 0 at p. Okay? So this expression here reduces to the integral. This part goes away. It's just the expected value under p of this object, okay, plus the remainder. Okay? So now we see that phi of p is phi of p hat plus something that is first order plus something that is second order. So that suggests that we use as our estimator this guy and replace the expectation with the empirical expectation. Okay, and that's how we come up with the one-step estimator. Now, you'll learn in 583, if you haven't taken it yet, that if we use cross-fitting, and I'm going to sweep under the rug what that is, you can find the expansion of your estimator, and it boils down to be, I forgot an OP. Here I have to put plus little OP1. So it's a normal term, okay, because it's the empirical mean of the influence function, but evaluated at p. And evaluated at p, this has mean 0 at p, and this is an expectation taken from the distribution of p, plus a remainder, plus a little OP1. Well, this remainder, then if we manage to make this remainder to be little OP1, then we have convergence to at rate root n. Okay, so all of this to say that this part here, this remainder here, is super important. It's what's driving double robustness. It's what all of double debias machine learning is about. Okay, all those buzzwords. It's all about handling this remainder, okay? And And okay, so the point is that if whether I convince you or not, this is the object that we want to find out. Okay, the phi1 of p is what we really want to calculate, the influence function. Okay, so now let's go again to our problem. So I have to repeat the problem because by now you probably forgot. So this is the example. Yes. I can't hear you. Hold on, because I have. Yes.
Like the unit is paid inside this division, or is there?
No, the solution is unique. The solution is unique. In this particular problem, the solution M is unique.
So what if like it's not unique? Is there?
If no, we can discuss that. It depends. I mean, if the functional that you want to estimate is a linear functional with representer that is orthogonal to the operator that defines the equation, then to the kernel of the operator, then you have uniqueness. I mean, let's not talk about that now because it's going on a different problem. I mean, I don't want to see. I'm using this as an example, but I don't want to get into the details of estimation of every example because I mean the reason I chose this one is because this one has a closed form solution. It's super simple. Okay, every single problem. What we are doing right now, I said facilitating inference. I'm not saying this is the end of the story. It's the beginning of the story, really. You know, when you get the influence function, from then on, you have to put a lot of effort trying to think how you estimate the nuisances and so forth, okay? But this is just to understand the structure. Okay. All right, so what parameter did I care to estimate? The parameter that I care to estimate in the problem with the measurement error was the mean of y. Okay, the mean of y has an influence function in ideal data that it's super easy. It's y minus its mean. Okay, because it's a linear functional. So it's just y minus its mean. Psi of q is the mean of y. Okay, that's psi1 of q. Okay, so now I told you that we have a template. Okay, that we can actually magically derive from the ideal data influence function, move into the observed data influence function, okay? A template that if you were to do it by hand, it would take you pages and pages, okay? Most of the time, all right? Okay, so how do you do it? Okay, now let's go back to the problem. In the problem, we had two sources, okay? On the first source, we had agreement on the marginal of V and X. Okay, remember that? The first source, the marginal of V and X. V was the mismeasure, the imperfect test. Okay, so we had agreement on that. In the second source, we had agreement on the distribution of V given Y and X. Correct? Okay, so the rule is the following. You give me your ideal data influence function. In this case, there is only one, because I have a non-parametric model for Q. There's only one data influence function. And you now have to decompose that ideal data influence function into a sum of two terms. Why two terms in this case? Because I had two sources, and in each source, I had only one alignment, okay? Otherwise, you will have to decompose it in as many terms as sources and alignments, okay? Sources times alignments, all right? Now, in this case, it's simple. Two sources and one alignment in each. So what I have to do is decompose it in such a way that if I align on the marginal of V and X, I have to have one term of the sum to be a function of V and X that has mean 0, because I'm not conditioning on anything. Function of V and X that has mean 0. In the second one, I had the distribution of V given Y and X, okay? So there, for the second term, I need a function of Y, V, and X, whatever intervenes in the conditional distribution, okay, which is V, Y, and X, that has, I need a function of V, Y, and X that has mean 0 given Y and X, okay? So it's always, you take whatever alignment you had, okay, and you now say, I need a function of the variables intervening in that alignment, okay, in that conditional distribution, such that when I condition on the variables that are in the conditioning event, it's equal to, has mean 0, okay? And in this case, it's very simple. What I have to do is add and subtract that magic MQ, Okay, why is that? Because if you remember, MQ by definition had mean zero given y and v, y and x. Okay, so that means that y, no, not mean zero, that mean equal to y given y and x. So again, MQ of Vx had the property that the expected value of this given y and x is equal to y. Well, then the expected value of all of these given y and x is 0. So this is a function of x, v, and y that has mean 0 given y and x. Okay? So this satisfies the requirement for one of the terms, the term that comes from the validation study. How about the other one? Well, the other one, we know that the expected value of m is psi. I proved you that a minute ago. Okay, so this is a function of x and v that has mean 0. So this is a function of x and v with q mean 0. So the first step of the procedure is that decomposition. We got it in no time. Okay. Now you may say, how do you find out? We have an algorithm to figure it out in general. I cannot describe the algorithm here, but we have an algorithm as well. Sometimes it's not so simple because the problem is intricate. Okay. All right. Now, how do you get to the observed data influence function? Look how easy. Look how incredibly simple it is. All you have to do is you take the piece that comprises that is coming from the first term, okay, the term that has to do with source 1. And if it comes from source 1, you have to always plug in the indicator of the source divided by the marginal probability of the source. Then, because in this particular case, you had alignment on a joint distribution, you didn't condition on anything, you just write down then this term. Okay? Now, the second one, you write the source divided, the indicator of the source divided by the probability. And then what you write here is what we call covariate shift. I'll give you in a moment an explanation of why this is the right thing in the intuition. So what you do here is you have, remember I had a distribution, I had a function of Vx and y that had mean 0 given x and y. Well, what I have to do is always write the q, okay, not the p, the q divided by the p, the marginal of whatever I am conditioning on, which is x and y, the marginal under q divided by the marginal under s equal to. Now you may say, wait a minute, you told me that you were going, and then you add that, multiply by the second term. Now you may say, wait a minute, this is, you have a p here, and now you have q's all over the places. How come? I mean, you have to write it in terms of p, not in terms of q. Well, in this case, it's no problem, because q is completely identified by p. Okay, the same as I can identify the mean of y, I can identify the mean of y given x. I can identify everything. Okay, so bear with me that it's true. I would have to do one more calculation, but it's true. The joint is identified. The m, of course, is identified because remember the m depended on the distribution in s equal to, okay, in the source 2 in the validation. So I just have to replace the q by whatever formula I get from the identification. Okay, that may be, you know, you may have to do calculations, but that's what it is. That's why it's all entangled. I mean, it's not straightforward, okay? Because the information is all over the places. Now, let me explain you why this is called the covariate shift and why this makes sense. This formula makes sense. So imagine for a moment that I told you that I whisper at your ear the function m. Okay, so I whisper at your ear the function m. Okay, so you say, well, I know that the expected value of m is psi. Okay, the expected value of m in source 1, because source 1 is the one where I took a random sample from Q, right? So what would I do? I would just calculate the mean of m in source 1. Okay, I would take the sample average in source 1 of the mean of m. Well, if I do that, the influence function for that estimator, the mean of m, will be this influence function. Okay, so this is what I would get if the oracle whispered at my ear this m, then I would get an estimator, the empirical mean of M, which would be my estimator of psi, and which would have influence function this, okay? But I wasn't whispered at my ear the M. I actually got the M from a second sample, okay, from the validation sample, right? And that M has bias. We said it has bias, right? So can I help myself with the data from the validation to fix that bias, to correct it? Well, I can, because look, for a moment, imagine that the distribution of X and Y was the same in source 2 as in Q, for the moment, okay? Imagine that, okay? So if I took the mean of Y minus my M hat in source 2, okay, the empirical mean, that would give me a hint whether I am offshot, overestimating M or underestimating M, okay? Because the mean of Y should be the mean of M, okay? So if I have an M hat, I should really, if this gives me very, very large, very, very large, I know that M was smaller than Y, than the mean of Y, so I should be uplifting, I don't know, adding something to my estimator. Otherwise, I should be, if this is negative, the mean of this is negative. But I don't want that because the mean in source 2 is not the same as the mean in source 1. And here I am calculating, what I'm doing is calculating everything in source 1, okay? So what I have to do is I have to adjust the distribution. The distribution of Y given X and V is the same in the two sources. In the Q and in the source 2. But what I have to do is to do the likelihood ratio to adjust, to bring back to the distribution of X and Y in source 1, okay? So this is what's called the covariate shift. We do the covariate shift to bring it back, bring this adjustment, that this is adjusting the bias of this guy when I have an M hat here, and it's adjusting it in the right way. Okay, yes, Thomas.
B given X and Y.
B given X and Y, sorry. B given X and Y, yes. B given X and Y. Yeah, I apologize. It's B given X and Y, and that's why because we are conditioning on X and Y, that's why we have to adjust here the covariate shift. X and Y are acting as covariates here. Okay? So that at least tells you that this formula is reasonable. Okay, I'm not telling you, how we get to the result. I told you a rule, a black box that you apply, and this black box is what I'm about to tell you now in complete generality. All right, so let me tell you what we did in general. Okay, what kind of problems we handle in general to try to establish generic results. Okay, so we have several sources, capital J sources, and in source S equal J, we are going to observe a subvector that we are going to call W supra J of W. Remember, W was all the vector. W supra J is a subset of the variables in W, okay? And in that source J, the distribution of Wj is P of Wj given S equal J, all right? Then what we are going to say is that distribution of Wj aligns, okay, agrees, okay, with the data generating Q of Wj, but not in all doesn't agree completely. It agrees only on certain conditionals. Okay, so what I'm going to do is, because I don't want to have a unique factorization, I'm going to first permute the vector Wj and now call Zj a permutation of Wj, whichever permutation corresponds to that particular alignment. And I'm going to say now, I'm going to write the distribution of Zj, which is is the Wj but permuted. I'm going to factorize it, okay, in this way. And I'm going to say then that the distribution of Zj given Sj agrees on certain factors, not on all of them, on some. Maybe one alone, maybe several, okay? Within one source, there has to be alignment with regards to one factorization, okay? But across sources, there could be mismatches, all right? Okay, But we want to be even more general than this. We want to say that perhaps maybe here, this Z bar means the history, okay? Z bar 2 is Z1, Z2, okay? Maybe we don't agree on the distribution of Z3 given Z2 for the entire conditioning event, for the entire set of conditional variables, but maybe for a subset of the Z bar 2s. So how do we express that? We say, look, our assumption is that the Q agrees with the P, okay, only for the Z's that are in a specified subset. And that subset, if it's empty, no agreement, okay? So this is writing it in complete generality. If this subset corresponds to the entire support of Z bar Kj, then it's full agreement, okay? And maybe this subset tells me only when, when one of the components of this variable is equal to 1, there is agreement. Otherwise, there isn't, okay? Everybody's with me here? Okay. So the main identification assumption that we make is that psi q depends on q only through the aligned components. Oops. And as I said, this generalizes Lee and Lütke. Lee and Lütke, essentially what they do is they have the entire vector, not just a subvector, the entire vector, they write the joint distribution without permuting, and they say in every single source, there is agreement with some components of that particular factorization. This, as you see, is more general, okay? All right, so now let's go to the main result. Okay, so now it's a lot of notation, but there's no way to write this in complete generality without delving into some notation, okay? But if you think of the example that we had before, this is not that difficult, okay? So suppose that Q aligns with P, and psi1q is an ideal data influence function that can be decomposed in this way. Now, this may look like crazy stuff, but it's not. This guy here is those functions that I wrote. Remember, I had two colors for two different components. So these are the functions of whatever, Z bar k, given Z bar k minus 1, that have to have mean 0. Okay, these functions have to have mean 0 only for the Z's that are in this guy, and multiplied by the indicator. So what is this? If this Z, calligraphic Z, is empty, it means that I don't have to, that particular term is 0. So only when there is agreement, when there is alignment, this guy is not going to be 0. And it may be that this thing is always 1 if this coincides with the support of this random variable. Otherwise, it will be just coinciding only on certain values of Z. It will be 1 only on certain values of Z. And for those values of Z, I require that I can write this function. I mean, I can decompose this with a function that has this property, okay? So if I am able to do this, if I have a full data, an ideal data influence function that decomposes like that, then look how easy. An observed data influence function arises just by the move that I told you before. You take the ratio of the indicator over the marginal probability, and then the covariate shift, and then add it this term, okay? So that's how you get an observed data influence function. Not only that, all observed data or fused data influence functions are constructed as in the previous slide, meaning that if you sweep over all the full data influence functions, the ideal influence functions, data influence functions, then you are going to sweep and you are able to decompose whichever ones you are able to decompose, those are the ones that are going to end up being observed, leading you to observe data influence functions. In particular, if you can find at least one ideal data influence function that decomposes in that way, then the parameter phi is pathwise differentiable, meaning it has an influence function, okay? Because otherwise it may not, okay? So these are details that I'm going to sweep under the rug because I don't think we have time. Now, our theorem also characterizes the fused data efficient influence function. So let me just give you one example. It's a bit complicated because it depends on whether the model Q is semi-parametric or non-parametric. We're going to do it in the simplest case where the model for Q is unrestricted, it's non-parametric. Okay, so in that case, imagine that I can decompose the psi with functions that have mean 0 given z bar k minus 1 on that set, multiplied by this guy. This is just some function of z bar k minus 1 that I could put inside. But they are not any function. They are functions of bound as conditional expectations of a unique h, okay, of a unique function h of w. Okay, w is the entire vector. So to find this h, you will have to solve an integral equation. There's a lot of stuff in here. Okay, and it may not be easy, but if you were able to find that h, then the fused data efficient influence function is of this form. Okay, so I'm not pretending that you understand all the details. I'm just telling you that very often this is not going to be simple. Okay, and the reason it's not simple is because the information is all entangled. Okay, with all these conditional expectations moving in one direction and the other, it's not simple. In the case of Alex scenario, where you have agreement with one factorization, everything it works like a charm. You can characterize the efficient influence function in complete generality much easier than this. Okay, and we have it in the paper as well. But in general, this is the complication. Okay, so I'm going to skip that. Let me give you, how much time do I have? 5 more minutes? Too bad. Okay, let me give you one. I don't know what to do. I mean, let's see. It's not fair because we started late. So, okay. Let me give you one example. Another example that is a bit complicated. I don't know how much I will be able to say. So suppose that you have your target population that is a target population from where you can only have access to a disease registry. Okay, so you only see the treatment and the covariates for those that are diseased. Okay, y=1 is diseased. Okay, so that's your target population, but that's the only thing you see. Then the alignment there is that, of course, you see for those disease, you see the distribution of the covariates and the treatment. Okay. Now, suppose that in that population, if I were able to measure y on everybody, ya and L on everybody, the L's would suffice to control for confounding. Okay, so that what you wanted to estimate is the ATE, and you have the usual formula and so forth. But of course, you cannot identify that from this because you only have the distribution of L and A given y=1. Okay, but now suppose that you have a second source, and I'm not going to discuss the substantive matter. We have discussed it in the paper, but suppose that in the second source, you are prepared to say that, okay, you measure ya and L, but you are prepared to say that only the distribution of y given a and L, in other words, the prevalence of disease within treatment and covariates, transports, okay, to the target population. And the parameter that you want to estimate is the ATE, okay? The usual ATE, assuming no one measure confounders, positivity, blah, blah, blah. Okay, so in this problem is embedded in a general structure that it's as follows. Suppose that you have a vector, the W vector, was B and D, where B was discrete. In this case, B was Y, okay, was binary, okay? But more general, suppose that B is discrete, D is anything. In our case, D was A and L, okay? Was treatment and covariates. And there are two sources. In one source, I'm prepared to assume that in source 1, the distribution of D given B equal B 0 and source 1 agrees with the target. And in source 2, the distribution of P given D for all values of D agrees. Okay? And now the question is, can I identify Q? Yes, I can identify it. If the probability of B equal B 0 given D is greater than 0. Thomas, you will like all of this because this is all entangled in the stuff that you do always. So, Okay, so this is just the marginal of D, okay? Once I identify the marginal of D, you know, via this formula, I identify the entire joint. Why do I identify the marginal of D? Because of course, the Q of D given B equal B0 is identified by this as alignment, and the Q of B equal B0 given D is identified by this alignment, okay? So this is a formula, you don't need to know it, okay? But it's identified, okay? So let me go to one more thing is that the alignments do not restrict P, meaning that if you give me a Q that satisfies these two because they agree, you know, you tell me that there exists a Q, and I say, does it exist? Does it always exist a Q? Yes, because if you give me this conditional and this conditional, I can always find a joint, so long as this holds. That has these two given conditionals. Okay, so that means that the alignments do not restrict P. P is a non-parametric model. Okay, the model for P. All right, they may have inequality constraints. I don't care about inequality constraints. It's all about equality constraints. Okay, all right. So now an over-identified problem. Suppose that you have D given B and B given D. Now suppose that B and D are continuous. Okay. And you tell me that the distribution of D given B and B given D align in the two sources. Now the question is that Q is over-identified, because what happens is over-identified by P. Why? Because I can write Q of D in this form, and I can write it in this form, choosing another B1 or B0. If you want, think of P as discrete with many levels so that we don't have to worry about measure theoretic problems, okay? But notice that if I replace the Q with the corresponding P, but at B0, I will get one functional. If I replace it at B1, I get another functional. So I have two different functionals of P that identify Q, okay? So that means that Q is over-identified. And the alignments, of course, severely restrict P. The model for P is severely restricted because whenever I replace the Q's by the P's, at B0 and at B1 have to be the same for all B0 and B1. Okay, so this is a very severely restricted model. Okay, so the question is there any example of this? Yes, suppose that in the first source, you have a case control study. Okay, so now you're prepared to assume that the distribution of confounders and treatment given outcome agrees, you know, with the target because you have a case control. But now in source 2, I mean, you care again about the ATE, meaning the risk difference, okay? But we know that if we want the risk difference, if we have a case control study, we need to know the prevalence. Otherwise, we cannot estimate ATE. But I'm going to assume something different. I'm going to assume that I have a source 2 from where I'm going to measure YA and L. But I'm going to assume not that the prevalence, the overall prevalence, but that the prevalence within levels of treatment and confounder agrees with the prevalence in the source. Okay, so it's a weaker assumption in a way. Okay, all right. So now we are in an instance where we have B given D, or I don't know, D given B, and B given D. Okay, so we have both. But if we are assuming, if we assume full agreement of the conditional prevalence, we have over-identification. Of course, you may say, why do you assume so much? No, I could assume just agreement on one value of A and one value of L, and I will have actually identification because of the other case, okay? But the point is that, again, if I wanted to estimate this, I have identification. And, okay, so can I do the influence function or no? You don't let me? Okay, well, anyways, in the first case, look how nice. I mean, I promise you that if you wanted to do it by hand, it would take you a while, okay? And you will be all confused and this and that. But in this case, it's super simple. I need a function. In the first case, remember, this is the agreement, the first alignment. So I need a function of D and B that is multiplied by the indicator of B equal B0 and has mean 0 given B equal B0. Well, this is the function, okay? Again, how did we come up with this? Trial and error? Not really. We have an algorithm to give us this, okay? But for the moment, believe me, this is the function that we want. And now we take psi minus that function, and it happens to be a function of b and d that has been 0 given d. Okay? So then, bingo, the influence function is this. Okay? And we have the influence function, beautiful, everything is all set. Okay? And now you only have to replace the q's by the p's and do your inference. Okay? In the case where we have over-identification, we have many influence functions. Why? Because for every influence function, we do this guy. Now we replace those indicators by q of b, q of b, divided by q bd. We have a function of bd with mean 0 given b. We have a function of bd with mean 0 given d now here. So these two give me one decomposition. But now there are many decompositions because the full data influence, the full data, the ideal data is not a, it's unrestricted, it's non-parametric, but the P data, the observed data model, is restricted, very restricted. Remember that I showed you that it's severely restricted. So I have many inference functions, and I get them by adding and subtracting a function of b and d that has mean 0 given b and given d. And those functions, we can characterize them. There's a paper that we wrote with Eric and Jamie a long time ago where we characterize these functions. Okay, one way of characterizing, I'm not going to go into the details, but then, you know, once we have these guys, bingo, here we have all observed data influence functions. These are all the observed data influence functions. And now, blah, blah, here is how we calculate the efficient influence function in this problem. Remember, in this problem, there's a lot of information, okay? And the efficient influence function, you calculate it like this. Remember, there was some conditional expectations that I had an h. Well, you know, this is the integral equation that you have to solve for the full data efficient influence function. It's the unique one. And then you plug it in here, blah, blah, blah. You get the efficient influence function. We don't have time to go through that. But let me say that if at least one of B or D is discrete, as it would be the case in the case control study where Y plays the role of B and is discrete, then this integral equation has a closed form solution. Okay, we can find the closed form solution. And Ellen did some nice calculations here of asymptotic relative efficiency for estimating the ATE. You know, when this is you know, relative to the case control. When we have a case control, here is where we align only, you know, we are assuming that we are aligning only on the cases. Here we are aligning only on the controls. There is, of course, less information because when we align only on the cases, we have just identification, okay? And there's much less information. Of course, you may say, why do I want this one? I don't want this one, actually, because this one brings me bias. It's imposing many more alignments than needed, okay, than we really need, okay? All right, so let me just conclude by saying a few more things. As I said, in our paper, we provide an algorithm for calculating you know, the decomposition that we need. And Ellen, the latest magic, incredible work of Ellen, is that she was able to characterize the remainder for P in the expansion, in this von Mises-Taylor's expansion, in terms of the remainder for Q. Okay? And that is fantastic because that tells us exactly what kinds of double robustness or multiple robustness we inherit from the full data problem and how many additional nuisance functions we have to estimate and whatever additional robustness we need, you know, we have, or more imposition. So this is actually very nice. She's now writing the paper. And we are working on extensions to alignments to other alignments other than conditional distributions. Right now, I just did, you know, the whole thing is assuming that the source is aligned with conditional distributions, but they may align with just conditional means or odds ratios or something else. And we think we know how to do everything. And if I had another hour, I would explain you how we derive that theorem and what is the kernel of the idea, but some other time. All right. Yes, but let me,
So it seems that there is like one true distribution of the source S, and so to interpret the asymptotics, is it as if I'm using data sets, but I'm maintaining the ratio of the data that I get from each source?
no, you are assuming that you have like a big random sample from all the sources, and you are assuming that the probability of each source is fixed, is whatever it is, that you have a fraction on each source. So it's a good point, because I'm not assuming, and this is something interesting to do as further work, we are not assuming that one source has size that as n goes to infinity, that source, the size of that source is negligible compared to the size of another source. No, what we are assuming that the sizes of all the sources are in such way that there is some, non-negligible fraction of each on each source, okay, of the data on each source. Yeah. Yes. Hold on, because I have a problem here. Okay.
Are you always able to find such a decomposition?
No, so yeah, that's a good question. So if you are not, that means that the observed data parameter is not pathwise differentiable. Okay, now we have not, this is a good point, because this is really the open question that we don't know how to answer. We don't have, actually we do. We have an algorithm. It's complicated. We have an algorithm that if you give me a full data influence, an ideal data influence function, I go through that algorithm and I can tell you, this influence function, this ideal data influence function actually gives you an observed data influence function. Now, you can imagine that if you go through all of them and every single one tells me no, 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 then there is no. Now, a question that we don't know the answer is it always the case under some regularity conditions? Because I'm sweeping under the rug here issues about the covariate shift to be bounded away from 0 and infinity. Okay, those are regularity conditions, just like when you have positivity and missing data. So these are, away from those assumptions. We are not able to tell if the mere fact that you have a parameter in the ideal data that is pathwise differentiable, that necessarily the observed data parameter is pathwise differentiable. We were unable to find an example where it wasn't, modulus the regularity conditions. We were unable to find one, but we don't know if